Let's work an example from the book now using the method from the previous video. This is problem number 48 from page 268. And it asks us to find the area underneath the curve, y equals 3x minus 2, over the interval from 2 to 5. Now using the notation from the previous video, the interval from 2 to 5 would be the interval from A to B. So A would equal 2 and B would equal 5. So the first thing we want to do is slice into n rectangles. And then the width of each rectangle is given by delta x, and the formula for that is b minus a over n, the width of the interval divided by n. So here, b minus a is 3. So the width of each interval is 3 over n. The right endpoint of r sub I is called x sub I, and the formula for that is a plus delta x times I. A is the left endpoint, 2. Delta x is 3 over n times I. So x sub I still has an I in it. Using the right endpoint approximation, the height of r sub I will be f of x sub I. I'm going to plug the right endpoint of r sub I into the function f to get the height of that rectangle. So I'm going to substitute x sub I, this guy, in to f. So that's 3 x sub I minus 2, or using this expression, that's 3 times 2 plus 3 over ni minus 2. But we can simplify that a little bit. That's 6 plus 9 over ni minus 2, or 4 plus 9 over n times I. And that represents the height of the ith rectangle. So the area of the ith rectangle is f of x sub I times delta x. It's the height times the width, the height times the base. So f of x sub I, we just found, was 4 plus 9 over n times I. And the formula for delta x was 3 over n. Distributing, that gives us 12 over n plus 27 over n squared times I. And then the upper, well, not the upper sum, but the right endpoint approximation, which is going to be the sum of the areas of r sub I. So we're adding together all n of those rectangles. That'll be the sum, I equals 1 to n, of 12 over n plus 27 over n squared I. And this sum right here is what we were calling the Riemann sum. Now, some folks don't necessarily want to go through this step by step. If you don't, then you can build directly into the formula for the Riemann sum, which is f of x sub I, the sum of f of x sub I times delta x, as I goes from 1 to n. So this sum right here is what this simplifies to using this formula. So let's now expand out that expression and substitute in some of these summation formulas. So we have the sum of 12 over n plus 27 over n squared I, as I goes from 1 to n. First of all, let's break this into two separate sums. The sum I equals 1 to n of 12 over n, plus the sum I equals 1 to n of 27 over n squared I. The 12 over n doesn't have any i's in it, so it can be factored in front. Same thing for the 27 over n squared. And then notice that each of those sums is in the form of one of these summation formulas. The sum of 1 is formula 1, and the sum of I is formula 2. So let's substitute those in. I'll have 12 over n. The sum of 1 is n, so I substitute that in, plus 27 over n squared times the sum of I, which is n times n plus 1 over 2. Well, I'll simplify a little bit, but we don't have to go crazy. In the first one, the n's cancel. In the second term, I can cancel an n, which will give me a 27n plus 27 over 2n. And now let's stop there. We don't actually need to get a common denominator. We did that in the previous video because I wanted to be able to substitute in 4 and 5. But here, we can just take this as our formula for the Riemann sum. So if we use n rectangles, then this is going to be the right endpoint approximation. We'll use n rectangles, use the right endpoint to find the height, and add them all together. So if I had 100 rectangles, I'd just be plugging in n equals 100 into this formula. But if we, of course, we want the exact area. And that's going to be the limit as n goes to infinity of the Riemann sum. So that's the limit as n goes to infinity of 12 plus 27n plus 27 over 2n. Now the limit of a constant is a constant. And here, when I take the limit of this rational function, I notice that the degree of the numerator is the same as the degree of the denominator, so the limit will be the ratio of the leading coefficients. 27 over 2. So if you get a common denominator, that gives you 24 plus 27 over 2, or 51 over 2. So the exact area underneath 3x minus 2 between 2 and 5 is 51 over 2.